now we are in the second lecture of transformer. Here we will see some more problems which were already been asked in GATE. So let us see the next problem. The third question is, for a specified input voltage and frequency, if the equivalent radius of a core of a transformer is reduced by half, the factor by which the number of turns in the primary should change to maintain the same no load current is. Okay, so and this question has been asked in 2014 S1. There are 4 alternatives given, and the question is asking about the no load current of the transformer. So let us make a transformer. Let us make a transformer, or let us make its equivalent circuit. The equivalent of transformer is this is a transformer. Okay, or let us make the equivalent circuit, because this is the block diagram. So let us make the equivalent circuit. So the equivalent circuit of transformer is like so. This is the equivalent circuit of transformer. This is collectively called Z1, and this is collectively Z2. Okay, Z2 dash, because we have shifted each and every component in primary side. Okay, now this one is the you can say core magnetizing. This one is the magnetizing coil, and this one is the core loss component. Okay, this here we apply voltage V1. Here we apply voltage V1, and here we get current I1. Okay, and here the voltage becomes V2 and current becomes I2. Okay, but suppose this side, secondary side, this is the secondary side referred to primary. This is the equivalent circuit of a transformer referred to primary side. Okay, and if the secondary side is open circuited, then I2 will be 0. Let me write this. If the secondary side is open, then the load current will be 0. The load current, and that is the load current here is nothing but this load. This will be I2. That is I2 will be 0. So now I1 will be nothing but this is the I0. You can say I0. Means this is the no load current. Okay. So now the primary current will be I1 will be nothing but I0. So I1 is primary current and I0 is no load current. Means no load current or open circuit current, you can say. This is the question is asking about the factor by which the number of turns in the primary should be changed to maintain the same no load current. If there is no load means the circuit is open. No load means the secondary circuit is open. Okay, so this you can say no load current or open circuit. This, so no load current, or you can say open circuit current also. Okay. Now the value of primary current will be equal to I naught. That I naught is flowing through this you can say this coil. Now the value of V1 will be, V1 is, what is the value of V1? So V1, V is, or you can say V1 is, the question is saying that the primary if the equivalent radius of core of transformer is reduced by half, the factor by which the number of turns in primary should change to maintain the same number of current, the same no load current. Okay, so V1 is equal to, what is V1m, the amplitude of primary voltage V1. So you can say V1m, because it is sinusoidal, so sinusoidal is sin omega t will also be associated, but I am writing only the amplitude. Okay, or you can say the RMS value. So V1 will be nothing but 4.44 Fn phi. So here n is n1, because we are calculating here in primary side, and you can say phi is flux flowing through the core of transformer, and F is the frequency. Okay, and the question is asking about the number of turns. The number of turns in primary should change to maintain the same no load current. Okay, now the no load current, since here the core is the core if the equivalent radius of core of transformer is reduced by half. Now the equivalent radius is reduced by half. So now suppose at first we apply V1 1. So in first case, if the core is not changed, so let us take if the core is not changed, case 1 here, case 1, when the core is not changed. Okay, when the core is not changed, when the core is not changed, means core is, the radius of core is as it is original. So let us take the voltage is V11. Okay, here that will be equal to 4.44 Fn. Now let us take here N1 1, because here we have added the suffix 1 for it is not changed. N11 phi m1. Okay, phi m1. So now if we write phi m1 as, so what is phi? Phi is the flux, and it is equal to the area of core multiplied by the flux density. So we can write here it as, it is nothing but 4.44 Fn, or let me write afterwards case 2. When the core is reduced to half, when the radius of core is here, the radius of core of transformer is reduced by half. When the radius of core is reduced to half. Now let us denote it as V12. Okay, so V12 will be nothing but 4.44 Fn12. Okay, phi m2. Okay, Now what is n? N is the number of primary terms, okay, and here n is the number of primary terms when core is reduced to half, okay. Now let us see what is the value of flux phi, okay. So let us write here what is the value of flux phi. So flux phi is from magnetic circuit, flux phi is nothing but it is mmf divided by mmf divided by reluctance. Okay, and what is the value of mmf? It is nothing but it is equal to Ni, where N is the number of turns and I is the current flowing in the coil, divided by this reluctance is denoted by R, and the value of reluctance R is nothing but L by mu A. So it is Ni divided by L by mu A, where L is the length of magnetic core and mu is the permeability of that core and A is the area, cross sectional area of that core. So now it will be nothing but Nia, N mu will go upside, so we can write here mu by L and Nia. Okay, so since mu by L this is constant, so we can write here phi is proportional to Nia, because N is the number of turns, I is current flowing through coil and A is the area. Okay, so phi is proportional to Nia. So now we can write here V1 will be nothing but it will be equal to again N11 and I1, you can say I11 here, or I1 because current is same, no load current is same, so I1 multiplied by area A. So now we can write here, from here we can write, let me write here itself. Now we can write V11, here let me write K Nia. This K is a constant. Okay. Now V11 will be nothing but 4.44 F N11. Okay, and in place of phi m1 we should write it as K multiplied by K N11 I1 A1. Okay, because area is here A. Now again here, from here V12 we can write here V12 will, sorry, here also let me write V11. Okay. Now V12 will be, so now V12 will be 4.44 F N12 N12 multiplied by K N12 I1 A2, because I is not changing. So I1 is nothing but I0. Okay. Now we have got what will be the value of V11 and what will be the value of V12. Now since here we can write since radius is here, radius of core of transformer is reduced by half. Radius is reduced by half. Since radius is getting reduced by half, so area of core will be. So what is the area of core? So area of core is nothing but it will be pi r square. Okay, it will be pi r square if it is a circular, if it is a cylindrical core. It is written that for a specified value of input voltage and frequency, if the equivalent radius of core of a transformer is reduced. So the core is a cylindrical core here, and that area is reduced, means that radius is reduced here. Radius of the core is reduced and area of core is pi r square. So A1 will be nothing but pi r1 square. Okay. A2 equal to pi r2 square, and as we can see, the radius is made half. So R2 will be nothing but pi R1 divided by 2 square. So what will be it? So it will be pi R1 square by 4. So pi R1 square by 4. And since it is pi R1 square by 4, so it is nothing but it is A2 will be A1 divided by 4. Okay, now it is okay. So A2 will be nothing but A1 divided by 4. Now let us write this side. Now let us write, let me mark it by green. So let us write this side. Now what will be the value of V11? So the value of V11 will be equal to 4.44 F N12 pi N11, sorry, it will be N11 pi M1. Okay, so it will be now, as I have calculated the value of phi. What is the value of phi? So if we put the value of phi as because if we put the value of phi as mu by L, n means kNIA, where k is some constant, so we can put the value of (4.44) F N11. Here we put k multiplied by k N I will be here I naught. Here I have calculated the value of so there is no need to write it again. So let me write it like this from here. So V11 will be nothing but 4.44 F. So it will be 4.44 K F. F is the frequency these are constant, and I naught, these all are constant, these all are constant, multiplied by n11 square, n11 square, okay, n11 square into a1, okay. So this is a constant term, this is a constant term, because here k is some constant, f is frequency is constant, I naught is constant, okay, because the question is saying that the primary should not change, the number of terms in the primary should change to maintain the same no load current. This I naught is no load current, so we don't have to change I naught, so this is a constant, okay. Now what will be V12? So let me write here what is V12. V12, okay. So V12 will be nothing but 4.44 F. Here also let me write in that fashion only, K F I naught, okay, K F I naught, N12 square, N12 square, okay, 80. So now this is again a constant, this is again a constant, okay. So if we divide these two, hence we can write V11 divided by V12, okay. So if we divide V11 divided by V12, then it will be nothing but it will be N11 square A1 divided by N12 square A2. Now N11 square A1 is A2 is A1 by 4, as we can see from here. So N12 square A1 by 4, okay. Now it will be 4 N11 square divided by N12. Now the voltage applied is same, because voltage is not changing, voltage will not change, because it is given that for a specified input voltage, here it is given that for a specified input voltage, so V11 and V12 both are equal. Now we can write here, since V11 is equal to V12, okay, because we are applying a specified voltage, some specified, so V11 will be equal to V12. So hence we can write, hence these two will cancel out each other, so 1 equal to 4 N11 square divided by N12 square. So from here we can write 2 N11 square by N12 square, or we can write here N11 by N12, okay. This whole square is equal to 1 by 4, okay. So it will give N12 nothing but 2 into N11. So the value of N12, what is N12? So N12 is the number of turns when we reduce the radius of core by just 1/2. So after reducing the radius of core, we have to increase the number of turns by twice the number of turns what was previously. So this should be the relation, okay. So now which one is correct? So correct option is, now the correct option is option number C, okay. So correct option will be option number C. Option number C. Next problem is a single phase transformer has no load loss of 64 watt as obtained from an open circuit test. When a short circuit test is performed on it, 90% it with 90% of the rated current flowing in the both LV and HV windings, the measured loss is 81 watt. Okay, the transformer has maximum efficiency when operated at. This question has been asked in GATE 2013 and there are 4 alternatives. So let us see which alternative is correct one. Okay. So no load loss means open circuit test. If the circuit is open, then there will be no load. So given that no load test, let me write no load test. And what we determine from no load test? We determine the constant losses, or you can say iron losses. So the iron losses means Wi. Let us write it by Wi. So let us write it by Wi. So Wi will be, Wi means you can say this is also called iron loss or constant loss. So iron loss, or it is also called constant loss. Okay, and this is given as 64 watt. Why it is called constant loss? Because it remains constant for a given voltage supply. Okay, for the rated voltage supply, it remains always constant. It doesn't depend upon load. Whatever load we are taking, it will always be constant. It will only change when the supply voltage is changed. Okay, that's why it is called constant loss. So now iron loss is given as 64 watt. Okay, and now another test is given, short circuit test at 90% of the rated load. So the next thing is short circuit test. Circuit test at 90% of rated current. Okay, so it is given. So from the short circuit test we determine the copper loss, or you can say we determine the losses in the winding of transformers. So we determine the copper loss. So WC, or we can say it as copper loss. Okay, so it will be nothing but I square into R equivalent, where I is the current flowing in the winding, in the equivalent winding, and R equivalent is the resistance of the equivalent winding. So let me write here, where I is the current flowing in the windings, and R equivalent is equivalent resistance of winding. Okay, now we can see copper loss is directly proportional to I square, means what current is flowing in the winding, the copper loss is proportional to a square of that. Okay, so now it is given that the current is flowing 90% of the rated current. So now we can write here that WC, it is given that how much it is given. Let me write the current, the rated current as IR. So it will be 0.9 IR. Okay, so 0.9 IR square into R equivalent. This is, and this is given as 81 watt. So this is given as 81 watt. Okay, 81 watt. So now from here we can see, this will be 0.81 I square R into R equivalent. This will be 81 watt. So I R square into R equivalent this will be 81 divided by 0.81 and this will be 100 watt. Okay, so the copper loss, this is a variable loss because it depends upon the current flowing in the winding. Okay, so this loss will when the rated current will flow, then the loss will become 100 watt. So now we can write from here WCR. CR means copper loss at rated current. Okay, so WCR will be 100 watt. Now now the question is asking about the transformer has maximum efficiency when operated at. So the question is asking about the current when the transformer has maximum efficiency. So let the current flowing be I. Let the current flowing be. Let the current flowing be I. Let me write it as I something I1 when or IM when the efficiency of transformer is maximum. Okay, now as we know that the transformer has maximum efficiency when the constant loss is equal to variable loss, or you can say the iron loss, the copper loss is equal to iron loss. So for maximum efficiency, WC means core loss, that must be equal to WI, iron loss. Okay, so here what will be the copper loss? So copper loss will be equal to this iron loss is also called core loss. Okay, because it is happening in the coil, in the coils, so it is also called core loss. So WC will be, what will be it? Since I have assumed the current as IM, I have assumed the current as IM, so WC will be IM square, okay, into R equivalent, and this must be equal to how much? This must be equal to 64 because it is a constant loss. So now this is our equation number 1 and this is our equation number 2. Now if we divide 1 by 2, dividing equation equation 1 by 2, how much we get? This is WCR and this WCR is nothing but this is IR square into R equivalent divided by IM square R equivalent, and this is given as 100 and this is given as 64. Okay, now R equivalent will cut each other. Now IR by IM will be nothing but it will be a square root of 100 by 64 and that will be 100 by 10 by 8. So IM will be nothing but 0.8 IR. Okay, that is IM will be equal to 80% of IR. Okay, means 80% of rated current. So if the current flowing in the transformer is, or you can say winding is 80% of the rated current, then the efficiency of transformer will be maximum. So which of the given options is correct? So option number C is correct one. Okay. At the last of the lecture, I would like to share one of the most important thing to you people, that if you like my video, then you must subscribe the video so that there is no need to search the new video which I upload. The automatic upload will come to you. What you have to do for this? It is very simple. There is a circular logo containing my photo is coming in right of me. You have to just click on that for subscription.